Okay, so yes, and as we can see here, our next talk is about coevolutionary heuristics for maximization of expected utility.
Test. There we go. Hi all, my name is Tom Willkens. I'm here presenting that work. Also done with my advisor, Jordan Pollack. And I come from the demo lab at Brandeis University. So we have, most of us probably are familiar with the basic genetic algorithm, which can be deployed for optimization purposes, where we start with some initial population. We have some test or objective function, which we might be trying to maximize or minimize. And then based on the performance of that population on that test, we might select new parents or members to persist to the next generation. We create that next generation, and then we continue in a loop until our problem is solved or approximately solved. But we run into a problem when we have certain types of problems with very large test sets. If the test set is too large, then it's not possible to evaluate every possible solution on every test, as the number of evaluations increases combinatorially. Also, we might have a case where we have tests that are very different from each other, probing different aspects of each member of the learner population. And so we need to make choices about which tests are most useful to evaluate. And this is something that might change over time as the learners evolve and improve. But when we have a setup like this, let me get one there. Yeah, there we go. All right. So for conditions like that, we would use techniques such as coevolutionary learning, where we must explore that space of tests. And so this involves evolution among two populations, the set of learners and the set of tests. This has many applications. It's a very broad paradigm. It can be used for designing physical systems. It's been used for the design of components of naval vessels. It can be used to design algorithms, such as the famous sorting networks of Danny Hillis. And also, this paradigm applies to agent design for self-play, for games like chess, backgammon, and Go. But we have problems unique to this method of problem solving, known as coevolutionary pathologies. These include over-specialization on one particular dimension or aspect of the problem at the expense of others, disengagement when members of the test population become either too difficult or too easy for the learners to make progress, and cycling between some set of previous strategies, failing to make progress. This results in loss of gradient and stable states. There are archive methods that have theoretical guarantees, but they're very costly and unreliable in practice, sometimes requiring infinite space. There have been recent attempts at developing heuristics for addressing these problems. One is the discovery of objectives via clustering algorithm. This is intended to maximize expected utility, which can be understood as average performance over that entire set of tests. Now, this clustering approach is a method of diversity maintenance and learner selection. So the intuition is that we identify unique skills among the learners, even if they don't have the highest fitness. So this is a procedure that clusters over the columns of this interaction matrix, where the rows represent the learners and the columns the tests. We use multi-objective optimization, such as NSGA2, on those derived objectives in order to pick the learners, and then a genetic algorithm is used for test generation. So, but experience with this method actually shows that it only leads to modest benefits. We still have the problem of the pathology of overspecialization. So experiments with different hybrid models led to the discovery that defining a sampling policy over a Q data structure for the test population actually yields some of the advantages that we get with those theoretical archive methods. And so now we propose that Q-based test generator for maximization of expected utility, which for short we call Q-mu. So here we use a different data structure for that test population. And so here's a visual schematic of how that algorithm works, where we could imagine a Q structure divided up into two portions, an active portion and a passive portion. Those are used to generate an interaction pool, which then is paired up against members of the learner population. So we have all of the active members are represented, as well as a sample from the passive portion. And then we generate a set of mutants using the active portion of the Q. And so the intuition there is to get some stability by retrieving some chance of getting information from the past, while still making progress in some direction of the learning process. And so once we have that pool, we determine which members of those pool are most informative relative to the learner population. And then that most informative member or set of members is moved to the front of the queue, which if it reaches the maximum size, you delete the oldest elements. So most informative, right? That's an ambiguous term. In this case, there's a theoretically grounded method in order to determine, relative to the structure of the problem, which members of those populations are most informative. And the method for doing that is to derive the distinction matrix from that original interaction matrix. In this case, this has binary outcomes where a 1 represents pass and a 0 represents a fail. This is pretty simple to implement. It just requires matrix arithmetic and then a competitive fitness sharing step where we divide each distinction made by the other number of tests that make that own distinction. And so that's how we get that notion of the unique distinction. And so then, summing across the rows of the distinction matrix, we arrive at a score for informativeness, and we might choose the most informative member of the population to move to the front of the queue. So we're going to look at results on a couple of benchmarks. The first one, this is a classic benchmark problem for coevolution. And so generally, if your algorithm doesn't do well on this kind of problem, it likely won't do well on more difficult real-world problems. In this case, we have learners and tests are both represented as real-valued vectors. In order to interact between the two, you fail a learner if the maximum dimension of the test is greater than the same dimension of the learner. So in the first case, because the greatest dimension of test A is that second dimension with a value of 0.5, it beats the learner who only has a value of 0.1. But the same learner on test B passes the test because it's higher in the fifth dimension than that test. The objective of this task is to maximize all learner dimensions. So we would want to have the highest number of dimensions or the highest value possible among the learner population's dimensions. And so this test in particular induces the pathology of overspecialization, where you tend to have members of the test population, if you're just using roulette selection, they will focus on a single dimension growing higher and higher. And so you will neglect certain dimensions of performance. And so here you have a visual example of Q-mu in action on a two-dimensional version of the numbers game. And so you can see the tests expand upon each one of those dimensions, corralling and moving members of that learner population in a direction approximately in the direction of the optimal trajectory for growth. And so at the end of this, we would want the learner's population to be maximal in all dimensions. And so this serves a fault tolerance function by leaving that trail of tests behind in decreasing difficulty in order to prevent regression. So you see at the end, it's rather close to that optimal trajectory. So here are some experimental results on a difficult version of the numbers game with a negative mutation bias in 5 dimensions. We use a couple baselines here, and the first is taken from the original doc paper, where the fitness function for the tests is just the sum of distinctions. The second baseline is a more advanced method, which uses fitness sharing and performs a linear combination of performance and distinction. So the idea is to get hard tests that are still informative. But if you look at the results on 2 variants of the numbers game, this results in over-specialization, where the y-axis is that minimum dimension value averaged over the population. You see the baselines plateau on the first problem and then actually degrade towards 0 on the second problem, whereas the QMU algorithm leads to consistent and steady growth. And so this is similar to those archive methods. The second task, pardon me, this is a well-established problem in the literature, the density classification task, which uses elementary cellular automata to classify bit strings. We want to determine if some initial condition of bit strings is majority 1 or 0, and we use the automata to evolve that condition to a final state. And so naive strategies would be like on the top, where essentially, no matter what you give it, it will just default to either classifying it as 1 or 0. More effective particle strategies incorporate and combine information from different portions of the bit string in order to arrive at a more accurate classification. And so you see that both of the baselines plateau, excuse me, at the default strategy, whereas the QMU algorithm attains a more steady growth, and with enough time, it discovers more effective particle strategies. And so finally, in conclusion, that summarizes the results given in the paper, where we see that the new QMU heuristic mitigates the problem of overspecialization and maintains a learning gradient. In more recent work, we found that QMU maintains adaptive complexity growth in a potentially open-ended domain using a finite state machine substrate, where the top graph is the total number of machines or states in each machine, and then the bottom is after applying adaptive pruning using the modes toolbox. And we still have different variants of QMU attaining a positive slope by the end of 10,000 generations. So future work would include implementing some sort of adaptive sampling policy. Currently, those QMU variants just use fixed policies sampling different proportions from the Q. Using some kind of reinforcement learning method on that sampling policy could allow it to be more performative across different domains. And then also, this could be incorporated as part of an outer loop, perhaps, with a reinforcement learning procedure on some sort of game playing task. So the goal would be to expand out into more complex domains to see how general and effective this new heuristic is. Thank you. That concludes my talk.